we know the probability in the canonical ensemble we define probability by Pj, which is function of n, v and t, is nothing but sum over states e to the minus beta Ej, where Ej is function of n and v, and beta is 1 by kVt. Now, Ej is nothing but we can write epsilon 1j plus epsilon 2j like this, and we have n number of particles in our system. So, it goes up to epsilon nj, where epsilon 1j is the energy of particle 1 in the jth state. Similarly, epsilon 2j is the energy of particle 2 in the jth state, and so on. Now, if we substitute the value of Ej into Pj, we get or if we substitute directly the value of Ej into the partition function q. So, canonical partition function q, we know the q is nothing but sum over j e to the minus beta Ej. Now, if we substitute the value of Ej here, we get sum over j e to the minus beta we can further reduce this expression like this. Okay. Now, if all the particles are the same, if all the particles are the same, then it is not necessary or not necessary to level them, right. So, we can omit 1, 2, 3 those terms. So, we can write q n number of terms. So, basically we have sum over j e to the minus beta epsilon j we have n number of terms. Okay. So, we can write Q like sum over j, where j is number of states, to the n, or we can write Q is Q to the n, okay, where Q is nothing but sum over e to the minus beta epsilon j. Note that here the epsilon j value depends only on volume, unlike that in Ej, where Ej was a function of n number of particles as well as volume V. So, here Q we define another quantity Q, small q, which is nothing but sum over j e to the minus beta epsilon j, and this Q is known as molecular partition function. Or partition function of a single molecule. Remember here we considered particles are distinguishable. Okay. So, for distinguishable particles we obtain the canonical partition function or partition function of n number of particles is q to the n, small q to the n, and for indistinguishable particle, when particles are indistinguishable, we have one factorial n term in the denominator. Okay. So, the beauty of this is we had a n body problem, we reduces the n body problem into n number of single body problems. Okay. Okay. So, we will discuss more next, we will discuss more about molecular partition function. So, we discuss more about molecular partition function. Okay, suppose we have total a number of distinguishable particles. So, out of this capital N number of distinguishable particles, so out of n number of particles, n1 number of particles are present in energy state epsilon 1. Okay, so n1 number of particles are present in energy state epsilon 1. Similarly, n2 number of particles are present in energy state epsilon 2 and so on. So, we can write sum over I Ni is nothing but capital N, which is constant. So, suppose this is our equation number 1 and sum over I Ni epsilon I is E total energy, that is also a constant, and this is our expression 2. Okay. Now a general configuration. So, now we are distributing capital N number of particles in different energy state. So, a general configuration can be achieved in W different ways. So, W we can write W is nothing but factorial N by N1 factorial, N2 factorial and so on. So, suppose this is our equation 3, where W here, W is the number of microstates corresponding to the given distribution. Okay. We will discuss more about this a little elaborately after some time. Okay. So, here W is the number of microstates corresponding to the given distribution. So, suppose for simplicity suppose we have three distinguishable particles, or rather three distinguishable, we can consider three balls, red, we say red is R, blue, we denote blue as B, and so we have yellow ball, and we define yellow by Y. So, suppose we have three balls and they are distinguishables. You can distinguish those balls by their colors, like one is red ball, one is blue ball and another is yellow ball. Okay. And we have three baskets. Okay. We have three baskets and we have three baskets. So, how many ways we can distribute the balls? Okay. So, in first case we have all three balls in basket 1. Okay. So, we consider three basket as basket 1 or small b1, small b2 and small b3, like these are the three baskets. this is B1, B2 and B3. So, we considered three distinguishable particles as three distinguishable as three balls, and we have three baskets, and our goal is to see how many ways we can put the balls into the baskets. Okay. Now, the first case, suppose we consider that all three baskets are present in basket 1. Okay. So, case 1, all three balls are present in basket B1. Okay, so we have three baskets here as we defined. So, we have three baskets B1, B2 and B3, and all three balls like blue, red and yellow. Okay. So, all three red, blue, red, blue, yellow. So, all three balls are present in basket 1. Okay. So, how many ways we can put? How many ways we can put these three balls in basket 1? That is W. So, W is, in this case, we have total three particles here. So, this is factorial 3, and all particles are in a given state. Here the state is basket B1. So, that is your N1 is 3 here, and N2 and N3, rather here B2 and B3 0 0. So, we get only 1. So, in only one way we can put all the three balls in basket B1. Next, we consider another case. The two balls are present in and one ball is present in basket B2. Let us see how many ways we can put. Okay. So, we have three baskets here. B1, B2 and B3, and two balls are present in basket B1. So, first we will put ball R and ball B in basket B1 and Y in basket B2. Next, what we will do, we will keep R as it is, we will interchange B and Y. So, we can put, we will put R and Y balls in basket B1 and B in basket B2. Next, we put B and Y in basket B1 and R in basket B2. Okay. So, how many ways we can distribute the three balls such that we get two balls in basket B1 and one ball in basket B2? That is three different ways. So, W here, according to the formula used in equation 3, so W is factorial 3 again by 2 factorial, 1 factorial and 0 factorial. So, we get 3. So, three different ways we can put three balls in two different baskets where two balls are present in basket B1 and one ball is present in basket B2. Now, we will consider another case, suppose case 3, okay. We have all baskets or each basket contains one ball. So, how many ways we can distribute? Okay, let us see. So, we have three baskets like B1, B2, B3. First, we put ball R in B1, ball B in B2 and ball Y in B3. Now, we keep R as it is, we will interchange ball B and Y and we get configuration, another configuration like R, Y, B, right. Similarly, we can put ball B in basket B1 and ball R in basket B2 and ball Y in basket B3. Now, we keep B again unchanged and we interchange R and Y. We get another configuration, right. Next, what we do? We put ball Y in basket B1 R in basket B2 and ball B in basket B3. Now, again we keep Y unchanged and we interchange ball R and ball B. So, we get configuration like Y, B, R. So, in 6 different ways we can put 3 distinguishable balls in 3 baskets. Okay. So, according to the formula we get W is factorial 3 by 1 factorial, 1 factorial, 1 factorial. So, we get 6. So, 6 different ways we can put 3 balls in 3 different baskets. So, what we expect? We expect higher the value of W, higher will be the probability, right. But we need to, this is true, but we need to satisfy equation 1 and 2. Okay. So, what I said is higher the weight W, higher will be the probability of the system to be found in the particular configuration. But we need to remember one thing, but equations 1 and 2 must be satisfied. Okay. So, what it says is we consider 3 balls in our examples. So, we cannot say okay we will use only 2 balls, okay, because the 3 balls we considered in our examples are nothing but particles. So, consider 3 particles. So, we need to consider all 3 particles. The total number of particles, that is capital N we use, is a constant term. Similarly, total energy or sum over I Ni epsilon I is constant. So, these 2 conditions must be satisfied. Then we need to consider higher the weight, higher will be the probability. Okay. So, we recall W is sum over n, n1 factorial, n2 factorial like this. So, we can take log ln W is ln n factorial minus ln n1 factorial minus ln n2 factorial, and it goes on. So, we can write ln W is ln n factorial minus sum over I ln ni factorial. Now, what we do, we use Stirling's approximation. Okay. So, by using so, what is Stirling's approximation? Stirling's approximation says ln x factorial is x ln x minus x when x is very large. So, this is Stirling's approximation. Okay. So, what we do, we will use Stirling's approximation because number of particles here is very large. Okay. So, we can use Stirling's approximation, and then we get ln W is n ln n minus sum over I ni ln ni minus ni, and then we have another term here. So, n ln n minus n. So, first term gives us n ln n minus n, and the second term gives us ni ln ni minus ni. So, we get ln W is n ln n minus sum over I ni ln ni plus sum over I ni. So, they get cancelled. So, we get ln W is n ln n minus ni minus sum over I ni ln ni. Okay. Next, what we need to do is we need to maximize W. Okay. So, in order to get the configuration for which W has its maximum, what we need to do? We need to do differentiation if we do differentiation, we get this. Okay. Or we can write like d ln W is sum over I del ln W by del Ni times dni. Okay. Again, since sum over I Ni is n, which is nothing but constant. So, we can write sum over I dni is 0. Similarly, sum over I Ni epsilon I gives us E, which is also a constant. From there we can write sum over I epsilon I dni equals to 0. Okay. Now what we do, we can write here dln w sum over I del ln w by del n I dni plus alpha my sum over, okay, so we can take alpha inside here plus alpha minus beta epsilon I times, okay, times dni, okay, where alpha and beta or minus beta rather are Lagrange's multipliers. Okay. So, what do you get now? Since dni is not equal to 0, so we can write del ln w by del ni plus alpha minus beta epsilon I equals to 0, and this is true for every I value. Okay. So, from there you can write minus ln ni plus 1 plus alpha minus beta epsilon I gives us 0. Okay. So, since number of particles in a given state, that is ni, is very large, we can omit 1. Okay. So, we can write minus ln ni plus alpha minus beta epsilon I is 0, because 1 can be neglected. In comparison to number of particles ni. Okay, so what do we get? We get ni is e to the alpha minus beta epsilon I. Okay. Now, or we can write ni is e to the alpha e to the minus beta epsilon I. Now, so this is the expression we have obtained. Now, sum over I, ni is nothing but total number of particles n. So, we can write sum over I e to the alpha e to the minus beta epsilon I is n. So, we get e to the alpha is n by sum over I e to the minus beta epsilon I. So, this is the value of e to the alpha we have got. Now, if we substitute e to the alpha into the expression of ni above, we get ni equals to n e to the minus beta epsilon I by sum over I e to the minus beta epsilon I, or we get ni by n, that is nothing but probability of ith state is e to the minus beta epsilon I by sum over I, where sum over I states e to the minus beta epsilon I. So, this is nothing but Boltzmann distribution law. So, we get Ni by n is sum of e to the minus beta epsilon I by sum over I, where I is nothing but states minus e to the minus beta epsilon I. So, if we consider degeneracy, okay, so we can write, so this is for some of our states, or we can write Ni by n is e to the minus beta epsilon I gi times sum over I, here I is sum over levels gi e to the minus beta epsilon I. Okay. So, if we consider degeneracy, we arrive at this expression where gi is the degeneracy of ith state. Okay. Next we consider, so what we need to do at this moment. Okay, so what we get, we discuss so far q which is a function of number of particles, volume and temperature, is sum over j e to the minus beta Ej, where Ej is function of n and v, and we deduced and we also deduce q nvt is nothing but q to the n for distinguishable particles, where q is molecular partition function e to the minus beta epsilon I, which is function of only volume, v is sum over levels So, what is our goal? Our goal is to calculate different thermodynamic properties. Okay. In order to do that, we need to calculate partition function of n number of particles or capital N. So, to calculate partition function of n number of particles or capital Q, we need to calculate small q, because we decompose the n body problem into n number of single body problems. So, our goal is to calculate now molecular partition function. If we know the molecular partition function, we can calculate capital Q. So, if we know small q or molecular partition function, we can calculate capital Q. Once we get the capital Q, we can calculate different thermodynamic quantities. So, our goal at this moment is to calculate small q or molecular partition function. Right. So, for this we consider the simplest system one can think of. Okay. The simplest system is ideal monoatomic gas. So, ideal means there is no interaction between the particle, ideal gas means, and then monoatomic means the particles, they do not have any vibrational and rotational degrees of freedom. They have only transitional degrees of freedom, electronic degrees of freedom and nuclear degrees of freedom. Okay. So, we consider the simplest system one can think of, that is ideal monoatomic gas. So, we consider, so next we discuss ideal monoatomic gas. Okay. So, a monoatomic gas gas has translational, electronic and nuclear degrees of freedom. The translational Hamiltonian is separable from the electronic and nuclear degrees of freedom. And electronic and nuclear Hamiltonians are separable to a very good approximation. So, basically the transitional Hamiltonian we can separate from electronic and nuclear Hamiltonians, and electronic and nuclear Hamiltonians are also separable to a very good approximation. So, we can write Q molecular partition function small q. Okay. So, small q we always will always use small q as molecular partition function. Okay. So, we can write q trans times q elec times q nuclear, where q trans is the translational partition function, q electronic is electronic partition function, and q nuclear is nuclear partition function. So, remember our goal is to calculate this. Goal is to calculate small q. In order to calculate small q, we need to calculate q trans, q electronic and q nuclear. Okay. So, once we calculate q trans, q electronic and q nuclear, we can calculate small q for ideal monoatomic gas. Once we get small q or molecular partition function, we can calculate capital Q. So, basically we are separating all degrees of freedom with some good approximations. So, our problem is now reduced to the calculation of translational partition function. In order to calculate the translational partition function, we consider particle in 3-dimensional box. Or rather cubic box we will consider. Of edge length, suppose edge length is A. Okay. So, the expression for energy in particle in 3-dimensional box is nx to the 2, ny to the 2 and nz to the 2 times h to the 2 by 8m a to the 2. This is the energy expression. So, what is the partition function? So, Q trans is sum over nx ny, or rather we can write like this, nx times ny times nz e to the minus beta epsilon nx ny nz, and the value of nx ny and nz varies from, starts from 1 to roughly infinity. Okay. So, this is the expression for, this is the general expression for partition function, and we are using the transitional energy in the epsilon value in Q trans or in transitional partition function. Okay. Very good. So, now we will substitute the value of epsilon nx ny nz here. We get Q trans So, if you substitute, if we suppose substitute the value of epsilon nx ny nz here, we get this. Okay. Or we can write Q trans is like this. Okay. So, here this three term, this three term, it represents, this is, or this represents the dimensionality of the box. So, we have used 3-dimensional box, so we get 3 in the power. Okay. Now, for or at room temperature, the successive term, now at room temperature, the successive terms in the summation differ so little from each other that the terms vary essentially continuously, and so the summation can be replaced by integral or integration. Okay, the successive terms in the summation differ so little. Okay, so the gap between the two transitional level is very small at room temperature compared to the value of KBT, that the terms vary essentially continuously, so the summation can be replaced by integral. So we get q, which is function of Vt, q trans rather, function of Vt, and if we do the integration, this is a very standard integration, we get twice pi m kBt by h to the 2 to the 3 by 2 times V, where V the volume of the box or a to the 3. So this is the expression for, translational partition function. Now we define a quantity lambda. So suppose lambda is h to the 2 by twice pi m kBt to the half. Okay, so if we consider lambda like this, so we write q trans is lambda to the 3, or rather V by lambda to the 3. Okay. So this is the expression for translational partition function. Okay. So what is lambda then? Okay. So lambda, what is the unit of lambda rather? Okay. So unit of lambda. Okay. So lambda is h to the 2. So lambda is h to the 2 by twice pi m kBt to the half. Lambda is h to the 2 by twice pi m kBt to the half. Now if we substitute the value of substitute the unit of h, m is the mass of the particle, and Boltzmann constant and temperature, we get is dimension of length. Okay. So lambda has the dimension of length. We can without doing this also we can assume the value of lambda we can assume, or we can really predict the value of lambda from the expression q trans. Okay. So we have q trans is V by lambda to the 3, and this is unitless quantity. So partition function has no unit. So partition function q trans is unitless. So partition function has no unit. So the lambda has unit of length. Thank you.